Hello guys, again this is Dr. Sunil Kumar. Welcomes you to this new video lecture. Actually in this new video lecture we will focus on the coordination chemistry of alkali metals. As all of you are aware that alkali metals previously you have studied as lithium, sodium, potassium, rubidium, cesium and francium. So these are the alkali metals which are supposed to be known by you. So the atomic number of lithium is 3 and sodium 11, potassium 19, rubidium 37 and cesium 55 and francium 87. The outermost electronic configuration or valence shell electronic configuration of all these alkali metals follows NS1, right? So there is a one electron which is present in s orbital of the each alkali metals. So as all of you know that when we go from top to bottom, means when we go from lithium to francium, the outermost quantum number which is here n is equal to 2, 3, 4, 5, 6 and 7 for alkali metals, right? So as the principal quantum number increases from top to bottom, it means the distance from the nucleus to outermost electron is increasing from top to bottom. It means the size, means atomic radius increases from top to bottom. Increases in the group. In the group. Because all of these alkali metals lies in group first elements. So all these elements form M plus type of cation through the oxidation of one outermost electron. So this is univalent cation. Univalent cation. Univalent cation. All these elements are electropositive in nature, and because of presence of +1 charge, means it has +1 oxidation state, +1 oxidation number. All the alkali metals have +1 oxidation number and they are all electropositive in nature, right? So if you think the ionic radius similar to the atomic radius, after releasing one electron from the outermost shell, the resultant cation Li plus, sodium plus, and potassium plus, rubidium plus, and cesium plus. Here we are not consider francium because of the radioactive and which has low abundance in the nature. So that is why we are interested to only lithium plus, sodium plus, potassium plus, and rubidium plus, cesium plus. The smallest size, the ionic radii of the lithium plus is the very low. So smallest cation. This is the smallest cation. Smallest cation. And this cesium plus and this Cgm plus is the largest cation in the group. So when we are consider the alkali metals, means in the group first, so there is always one initial metal, that is lithium, which is the smallest in size, and cesium, which is largest in the size of this group, right? So next, as you know that lithium plus is the smallest size cation in the alkali metal groups, and mostly all alkali metal cations exist as a electropositive because of +1 oxidation state. So they forms all ionic compounds, means all alkali metal cations form ionic compounds. So you can think that Li plus, sodium plus, potassium plus may form ionic compounds like that. If there is a fluoride ion, so which is a halide ion, so all compound forms like LiF, NaF, and Kf, lithium fluoride, sodium fluoride, and potassium fluoride. So all these are ionic compounds. Ionic compounds means once it is dissolved in H2O, it forms ions like Li plus aqueous plus F minus aqueous. Because of the presence of cation and anion in the aqueous systems, all ionic compounds are dissolved in polar solvents like H2O. But what is the aqueous chemistry of the alkali metal cations? The alkali metal cations remain in hydrated state in the aqueous system. Alkali metal cations, alkali metal cation remains in hydrated phase in aqueous solution. In aqueous means H2O solution. Hence, we can say that alkali metal cations form MH2O का whole n, and this is plus charge. So this is what is called a different type of ion is called complex ion. This is called complex ion. Complex ion, in which there is a one central metal ion. Here M stands for lithium, sodium, potassium, etc. So this square brackets consisted of a central metal ion and surrounded by H2O with a definite number, which is N. N stands for 1, 2, 3, 4, 5, 6, etc. It is a definite quantity. So depending on the nature of M and depending on the number of N, actually decides what will be the resultant complex ion and what will be the geometry of this complex ion. So that will be discussed later. So suppose if you have a complex ion, so that is MH2O whole N and overall positive charge, because all alkali metal have +1 charge. So if you think M, lithium, sodium and potassium, then this M may be lithium H2O plus charge. In the case of lithium metal cation, so N is actually here 4. And in case of sodium and potassium, like sodium H2O whole 6 plus, or potassium H2O whole 6 plus. In case of rubidium and cesium, if M is a rubidium, then Rb H2O का whole 6 to 8, any value may be. And if there is a cesium H2O का whole 6, here there is not a whole 6, it will be 12. What you have observed is that in case of lithium metal cation, so there is only 4 H2O molecule which surrounds lithium cation. In case of sodium, so there is a 6 H2O molecule which surrounds sodium cation. In case of potassium, there is a 6 H2O molecules surrounds potassium ion. But in case of rubidium, there is a 6 to 8 H2O molecule. Minimum it may be 6, maximum it may be 8 H2O molecule which can surround rubidium cation. In case of cesium, there is a 12 H2O molecule which surrounds cesium cation, right? What is the what inferences here is that this is called an coordination number. Coordination number. If there is a coordination number 4, then it has the geometry tetrahedral. If coordination number is 6, then the geometry is octahedral. If coordination number is 7, then square prism, and if coordination number is 12, then higher order geometries is possible. So you can say that depending on the hydration number or depending on the coordination number, we can get different type of geometry in alkali metal chemistry. So all the alkali metals remains equated, hydrated in the aqueous solution. So what inferences here is that actually alkali metal cations form a complex ion, and that complex ion is basically coordinated ion. Here two type of species is present. One is metal. In every hydrated complex ion, there is one metal ion, and another one is called a ligand. So ligand is a chemical species which have a capacity to donate a pair of electron to the metal which have a vacant and suitable energy orbitals. So in this case, in this complex ion, M is metal ion, which is called Lewis acid. So that is called Lewis acid. Lewis acid, and ligand is called Lewis base. Lewis base. So coordination chemistry is nothing but it is the interaction of Lewis acid with respect to the Lewis base. So the reaction of Lewis acid with Lewis base is called coordination chemistry. Lewis acids, actually all alkali metal cations are Lewis acids because of positive charge. So it is a deficient species and it can accommodate a pair of electrons. So it can act as a Lewis acid, right? So Li plus and Cgm plus, the hard Lewis acid, smallest alkali metal cation is lithium plus, which is a hard Lewis acid. So that is hardest, you can say hardest Lewis acid. And in the respective group, Cgm plus, lowest hard alkali metals is Cgm plus. So the most important hard metals in the group is lithium plus, and lowest degree of hardness is observed in Cgm plus because of the large size, and lithium plus because of the small size it is a hard Lewis acid. So hard acid prefer hard base and soft acid prefer soft base in the coordination chemistry, right? So ligand should have also hard bases character. As per, you can think that H2O in the coordination chemistry, H2O is designated as aqua. So this is called aqua, AQUA, aqua. And the structure of H2O is OH. So there is a lone pair of electron. There is a two lone pair of electron. So this is electron sufficient species. This is electron rich species. It can be donated to the electron deficient species. So Li plus is electron deficient and aqua ion is electron rich species. So this is electron rich. It has donor sides. So this oxygen is called donor atom. So donor atom. And because of presence of two lone pairs, so it can act as a donor centers, donor sites. And this is lithium plus. It is because of positive charge, it is electron deficient in nature, and it has a suitable orbital to accept a pair of electrons. So this is what we call it as acceptor cation. Acceptor means Lewis acids are acceptor in nature, while Lewis base are donor in nature. Lewis acids are acceptor in nature. Lewis acids are acceptor in nature, while Lewis base are donor in nature. Right. So what inferences is that when we talk about the coordination chemistry of alkali metal cations, so then alkali metal cations are regarded as hard acids, and which is Lewis acids, and H2O, which has oxygen atom in the present in the structure, so that is electronegative atom, and which has also a pair of electrons, so it can be donated. Means what is the coordination chemistry here is that if there is a M cation, so if there is a metal cation, if it is in the environment of ligand, then suppose in the aqueous system O, this is the structure of H2O, and here a pair of electrons. So this pair of electron can be donated to acceptor Lewis acid and form a special type of bond, and this bond is called coordination bond. Coordinate bond, right? So in the coordination chemistry, so there is actually different type of bonds, that is coordination bond, yeah, coordinate bond, and similar to the covalent bond and ionic bond. So because of uh, donor nature of ligand, here pair of electron is donated to the Lewis acid, that is metal cation, so the bond is formed coordinate bond. So Lewis acid plus Lewis base, so form coordination compound, coordination compound, right? And this, the coordination compounds may be either positive, negative, or neutral. So it means there is a complex ion, it may be positive, negative, or neutral. So positive means positive complex ion, and negative means negative complex ion, and neutral means neutral complex ion, neutral complex. So Lewis acids, when react with Lewis base, form coordination compounds. So this is the coordination chemistry. And Lewis acids, basically in our case, alkali metals, and Lewis base, in initial system there is H2O, because all alkali metal ions remains in hydrated in the aqueous system. So that is why here we have considered H2O. So that is aqueous system is a ligand, and M means Li plus is a Lewis acid. So that will form LiH2O, a whole 4, and overall positive charge. Because the size of the lithium plus cation can accommodate 4 water molecules, right? So in the lattice, so that is why it has 4 coordination number. This indicates coordination number. This complex ion has 4 coordination number, 4 coordination number. And if there is a 4 coordination number, then the geometry which is obtained as tetrahedral, right? So in this way, Lewis acid and Lewis base react to form coordination compound, and coordination compounds may be complex ion. Complex ion may be positive complex ion, negative complex ion, and neutral complex compounds. So in the later and next video, I will discuss in detail the coordination chemistry of alkali metal.